Pressure relief, general. This section covers the selection, design, and arrangement of pressure-relieving devices. Relief requirements, comments on API RP 521, general. A pressure system can be protected by one or more relief valves, provided it is ensured that the system remains open under all conditions. It shall be established that blockage cannot occur due to valve closure, freezing, solidification, fouling, sublimation, damage of internals, etc., which could cause a section of the system to become isolated with no means of overpressure protection. For each relief device, the applicable causes of relief action and the resulting relief requirements shall be determined. The data for all pertinent relief conditions shall be recorded on a relief valve calculation sheet and in a safeguarding memorandum. The possible causes are listed in API RP 520, Part 1, Table 1. A more detailed description of the causes of relief action is given in API RP 521, Chapters 2 and 3. For the case of excess flow from a high-pressure source, high-pressure, low-pressure interface, the largest contribution of either the fully open control valve or the fully open bypass valve shall be taken into account. The calculation shall be based on the worst-case situation. Typically, this will be 100% vapor breakthrough, no liquid, and shall be made for the actually installed valves. For the highly improbable event that gas breakthrough takes place when both control valve and bypass are fully open, the capacity of the relief valve shall be such that the downstream pressure shall not exceed the hydrotest pressure of the system, taking into account any differences between the hydrotest temperature and the maximum operating temperature. In addition to the causes stated in API RP 520, and API RP 521, the emergency releases under startup and shutdown conditions shall also be considered since they can be more severe than at design operating conditions. In liquid full systems, where no vapor buffer is present, relief valve chatter, i.e., rapid opening and closing of the valve, can be violent and very destructive due to its high frequency. It can easily result in damage to the relief valves themselves and to piping components. Therefore, the need for liquid relief in the event of blocked outlets should be obviated by matching the design pressure of liquid full systems to the pressure of the blocked outlet case. Pressure relief, general. This section covers the selection, design, and arrangement of pressure-relieving devices. Relief requirements, comments on API RP 520-521, general. A pressure system can be protected by one or more relief valves, provided it is ensured that the system remains open under all conditions. It shall be established that blockage cannot occur due to valve closure, freezing, solidification, fouling, sublimation, damage of internals, etc., which could cause a section of the system to become isolated with no means of overpressure protection. For each relief device, the applicable causes of relief action and the resulting relief requirements shall be determined. The data for all pertinent relief conditions shall be recorded on a relief valve calculation sheet and in a safeguarding memorandum. The possible causes are listed in API RP 520, Part 1, Table 1. A more detailed description of the causes of relief action is given in API RP 521, Chapters 2 and 3. For the case of excess flow from a high-pressure source, high-pressure, low-pressure interface, the largest contribution of either the fully open control valve or the fully open bypass valve shall be taken into account. The calculation shall be based on the worst-case situation. Typically, this will be 100% vapor breakthrough, no liquid, and shall be made for the actually installed valves. For the highly improbable event that gas breakthrough takes place when both control valve and bypass are fully open, the capacity of the relief valve shall be such that the downstream pressure shall not exceed the hydrotest pressure of the system, taking into account any differences between the hydrotest temperature and the maximum operating temperature. In addition to the causes stated in API RP 520 and API RP 521, the emergency releases under startup and shutdown conditions shall also be considered, since they can be more severe than at design operating conditions. In liquid full systems, where no vapor buffer is present, relief valve chatter, i.e., rapid opening and closing of the valve, can be violent and very destructive due to its high frequency. It can easily result in damage to the relief valves themselves and to piping components. Therefore, the need for liquid relief in the event of blocked outlets should be obviated by matching the design pressure of liquid full systems to the pressure of the blocked outlet case. Fire case requirements. Equipment shall be protected against high pressure due to fire under the following conditions: if the equipment is located in an area where a sustained intense fire might occur. If it is conceivable that the equipment is blocked in without having been emptied first when such a fire occurs. An exception to both above may be made for small capacity, 500 liters, equipment containing liquid, which is non-toxic and has an initial boiling point higher than the maximum ambient temperature. During a fire, all input and output streams to and from the fire-affected equipment and all internal heat sources within the process are assumed to have ceased after fire detection and operator intervention. This may require ESD valves to be located appropriately. Potential fire areas shall be identified and clearly shown on a plot plan. The fire areas shall be numbered, and each number shall be indicated on the relief valve data sheet. For process units, a typical fire area of 300 m² should be assumed, depending on the drainage design of the plot. The height of the flame to be considered shall be 8 meters from grade or a platform on which liquid can accumulate, concrete platform. For buildings or offshore facilities, the concept of fire areas is replaced by one of fire compartments segregated by fire walls or floors. The area of these compartments is usually determined by fire containment requirements. If the equipment is already designed to be protected against operational emergencies by a relief valve, the same valve may serve for the fire case, provided it is of adequate size for all emergency cases. Vapor relief requirements in the event of fire should be based on the heat absorbed by the internally wetted surface area of the vessel, considering the effects of liquid vaporization and expansion and vapor density change. In addition to the vessel, the surface area of associated piping and equipment should be included. For the purposes of these calculations, the liquid level in the process vessel should be based on the normal liquid volume, including any liquid draining down from the internals of the vessel. Although firewater deluge provides additional protection, no allowance shall be made for active fire protection facilities when calculating the relief rate. However, with the approval of the principal, allowance may be made for fire protection systems, e.g., fireproof insulation, as stated in API RP 521, Table 5, if it is ensured that the insulation is resistant to fire heat and to the impact of fire water jets and jet fires. Piping within process or utility boundaries does not normally require relief valves sized for fire relief, but relief may be required for thermal expansion in liquid full systems. Where possible, the design of a facility should avoid blocked-in sections of pipework. Requirements for plate and printed circuit heat exchangers. Essentially, the considerations given in API RP 521 with respect to shell and tube heat exchanger failure also apply to plate and printed circuit heat exchangers. Although both sides of the actual exchanger will have the same design pressure, this may not be the case for other equipment on the low-pressure side, which may be subjected to overpressure. This shall be taken into account when sizing the relief device. For a plate and printed circuit heat exchanger, the maximum relief rate shall be based on a complete rupture running longitudinal to a corrugation. It is then necessary to consider the particular arrangement of the exchanger in question to determine the maximum number of inlets that are connected to the corrugation. The total cross-sectional area shall be calculated, allowing for twice the cross-sectional area of each inlet connected to the corrugation. Pressure relief. Thermal expansion relief valves, HERVs. Thermal expansion relief valves are required in liquid full systems if the system can be blocked in and subjected to heat input from the atmosphere or process. The theoretical pressure rise for most liquid systems lies in the range 5 to 15 bar for each degree centigrade of temperature increase. In practice, the theoretical pressure rise is not attained because systems are rarely totally liquid full and usually have small leakages through valve seats or gaskets. Calculations of the pressure rise are thus of little use in formulating realistic guidelines for the application of thermal relief valves. The following factors should be considered before deciding not to fit TURVs. Is the linework or equipment continuously in operation and thus unlikely to be isolated without being depressurized and drained? Most process equipment and piping is in this category. Is the liquid non-toxic and non-corrosive, and does it have an initial boiling point higher than the maximum ambient temperature? Is there a weak point in the system, such as a flange where expansion could relieve pressure without unacceptable consequences? Is it unlikely that the system will be totally liquid full, i.e. to more than 95%? Has the release a safety or environmental impact? As a general guide, TURVs are not needed for process plant piping, storage or transport piping sections which are not normally shut in for operational or emergency purposes, lines in which there is normally two-phase flow, systems which are not totally liquid-filled, i.e. less than 95% liquid. TURVs are normally fitted to the cold side of heat exchangers, which can be blocked in, sections of piping containing more than 500 liters of LPG or toxic liquids, which could be blocked in, piping in storage areas or transport lines, which will be regularly blocked in during normal operation, to protect against pressure rise due to solar heating or heat tracing. All sections of cryogenic piping, operating below ambient temperature, which can be blocked in irrespective of whether this is routinely done or not. In all cases, operating procedures should be such that overpressure due to thermal expansion cannot occur, even when a relief valve is fitted. This can be done by prescribing drainage of a small quantity after a pipe section has been blocked in. In this case, if allowed by the code, the set pressure of the TURVs may be 110% of the maximum allowable working pressure. This at least guarantees that the maximum allowable working pressure is not exceeded by more than 33%, and that during normal operation, the TURV will not operate and cause operational mishaps such as liquid spillage, permanent leakage, valve chatter, etc. The standard TURV size for piping systems is 25 by 25 millimeters flanged with a minimum orifice area of 0.71 centimeters. Bronze valves, which are allowed for water service only, may have screwed connections. The use of instrumented protective functions. The conventional approach to overpressure protection of piping and pressure vessels is to utilize two totally independent forms of protection. The first is a pressure control system. The second utilizes relief valves sized to relieve the pressure to a safe location if the first system fails, and is a complementary requirement dictated by the code and local authority regulations. This implies that normally relying solely on control is not permitted. In specific circumstances, it may be highly desirable to limit or even to eliminate emergency relief, since the flare relief system will become disproportionately large and expensive, or the environmental impact of such a relief would be unacceptable. In these cases, the level of protection afforded by a relief valve may be complemented with an instrumented protective function. Complete substitution of relief valves by an instrumented protective function can rarely be justified unless RVs are impossible or impractical. It should be recognized that local regulatory authorities may either prohibit instrumented protective functions as a substitute for protection by RVs, or demand to approve the design before issuing a certificate of fitness. Typical examples of the application of instrumented protective functions are equipment connected to a multiple well system. The design pressure of the equipment will normally be lower than the shut-in pressure of the wells. Therefore, overpressure protection to guard against shut-in of the wells shall be provided by a combination of an instrumented protective function and a mechanical relief system. Equipment located in remote areas where the environmental impact of a relief event would be unacceptable. In these cases, the reliability and availability of the instrumented protective function should be such that the probability of failure on demand is minimized. Equipment that contains hazardous materials. If the release of these materials due to a relief event would be unacceptable from a safety or environmental point of view, an instrumented protective function may be used to prevent the overpressure event. In all cases where an instrumented protective function is used as part of the overpressure protection system, it should be ensured that the design of the instrumented protective function meets the requirements of international standards for functional safety, e.g. IEC 61508 and IEC 61511. The reliability and availability of the instrumented protective function are demonstrated through appropriate safety integrity level (LSIL) assessments. The instrumented protective function is subjected to regular testing and maintenance to ensure its continued performance. The use of instrumented protective functions requires careful consideration of the specific process conditions and potential hazards. It is essential to conduct a thorough risk assessment to determine the suitability and reliability of the instrumented protective function in providing the necessary level of protection against overpressure events. Pressure relief device selection. The selection of relief devices for pressure systems involves considering various factors to ensure that the devices operate effectively under all potential overpressure scenarios. The following criteria should be used when selecting relief devices. 1. Type of relief device. The selection between different types of relief devices, such as spring-loaded pressure relief valves, pilot-operated relief valves, rupture discs, or a combination of these devices should be based on the specific requirements of the system. Each type has its own advantages and limitations. For example, spring-loaded pressure relief valves are suitable for most applications and are reliable. Pilot-operated relief valves are used for high set pressures and large relief capacities. Rupture discs provide instant relief but must be replaced after activation. Set pressure and overpressure. The relief device should be set to open at a pressure slightly above the maximum allowable working pressure, MAWP, of the system. The allowable overpressure, which is the pressure increase above the set pressure during a relieving event, must be considered to ensure the system's safety. 3. Capacity requirements. The relief device must have sufficient capacity to handle the maximum expected relief load. The capacity is determined based on the most severe overpressure scenarios identified during the hazard analysis, such as fire exposure, blocked outlet, or control valve failure. 4. Operating conditions. The relief device should be suitable for the specific operating conditions of the system, including operating pressure and temperature, nature of the fluid, gas, liquid, two-phase flow, toxic, corrosive, etc., operating frequency, and duration of relief events. Material compatibility. The materials of construction for the relief device must be compatible with the process fluid to prevent corrosion, erosion, or other forms of degradation that could impair the device's function. Special consideration should be given to fluids that are highly corrosive or toxic. 6. Response time. The relief device must respond quickly enough to prevent the system pressure from exceeding safe limits. Rupture discs, for example, provide instantaneous response, while spring-loaded and pilot-operated valves may have slightly slower response times. 7. Installation considerations. Proper installation is crucial for the reliable operation of relief devices. Factors to consider include orientation and mounting of the device, accessibility for testing, maintenance, and inspection, proper venting or piping of the discharge to a safe location to prevent harm to personnel or equipment. 8. Code and regulatory compliance. The relief devices must comply with applicable codes, standards, and regulations such as ASME Boiler and Pressure Vessel Code, API Recommended Practices, and local jurisdictional requirements. Compliance ensures that the devices meet minimum safety and performance criteria. 9. Back pressure. The effect of back pressure on the relief device must be considered, as it can influence the opening pressure and flow capacity. There are two types of back pressure. Built-up back pressure occurs downstream of the relief device due to the resistance of the discharge piping system. Superimposed back pressure exists on the outlet side of the relief device before it opens. 10. Reliability and maintenance. The selected relief device should have a proven track record of reliability and should be easy to maintain. Regular testing and maintenance are essential to ensure that the device remains in good working condition and will perform as expected during an overpressure event. By considering these factors, the appropriate relief device can be selected to provide effective overpressure protection for the pressure system, ensuring the safety of personnel, equipment, and the environment. Pressure relief. Relief device design considerations. The design of relief devices involves careful consideration of various factors to ensure their reliable and effective operation under all possible overpressure scenarios. The following are key design considerations for relief devices. 1. Relief device location. Relief devices should be located as close as possible to the protected equipment to minimize pressure drop and ensure prompt response. Devices should be installed in accessible locations for easy inspection, testing, and maintenance. 2. Inlet piping. The inlet piping to the relief device should be as short and straight as possible to minimize pressure losses. The diameter of the inlet piping should be at least equal to the nominal size of the relief device inlet. Avoid abrupt changes in direction and the use of fittings that can cause turbulence. 3. Outlet piping. Outlet piping should be designed to handle the maximum discharge rate without causing excessive back pressure. The diameter of the outlet piping should be at least equal to the nominal size of the relief device outlet. Ensure that the discharge is directed to a safe location, such as a flare system or a vent stack, to prevent harm to personnel and equipment. 4. Discharge to atmosphere. When discharging to the atmosphere, ensure that the relief device is equipped with a suitable deflector or muffler to minimize noise and prevent the ejection of liquid or debris. The discharge point should be located away from personnel areas, air intakes, and ignition sources. 5. Back pressure effects. The design should account for both built-up and superimposed back pressure, as they can affect the performance of the relief device. Ensure that the relief device is selected and set to operate correctly under the expected back pressure conditions. 6. Reaction forces. The discharge of a relief device can generate significant reaction forces. The piping and supports should be designed to withstand these forces without excessive movement or damage. Consider the use of anchors and guides to control the movement of discharge piping. 7. Temperature considerations. Relief devices should be designed to operate effectively over the entire range of temperatures expected in the system, including during relief events which may cause temperature fluctuations. Materials of construction should be selected to withstand these temperature extremes without compromising performance. 8. Material selection. The materials used for the relief device and associated piping should be compatible with the process fluid to prevent corrosion, erosion, and other forms of degradation. Consider the potential for hydrogen sulfide, H2S, or other corrosive agents when selecting materials. 9. Dynamic stability. Relief devices should be designed to avoid dynamic instability, such as chatter or flutter, which can result from rapid opening and closing cycles. Proper sizing and selection of the relief device can help mitigate these issues. 10. Flow characteristics. The flow characteristics of the relief device should match the requirements of the system, ensuring that the device can handle the maximum expected flow rate without exceeding allowable pressure limits. Use appropriate sizing equations and methodologies to determine the required orifice size and ensure adequate capacity. 11. Multiple relief devices. In some cases, multiple relief devices may be required to provide adequate protection. These devices should be designed to operate in parallel or series as needed. Ensure that the combined capacity of multiple devices meets or exceeds the required relief rate. 12. Environmental and safety considerations. The design should minimize the release of hazardous or toxic substances into the environment. Consider the use of scrubbers, flares, or other treatment systems to handle the discharge safely. 13. Instrumentation and monitoring. Consider incorporating instrumentation to monitor the status and performance of relief devices, such as pressure and temperature sensors. Remote monitoring and control systems can enhance safety by providing real-time data and enabling prompt response to overpressure events. 14. Maintenance and testing. The design should facilitate regular maintenance and testing to ensure the ongoing reliability of the relief device. Consider the use of features such as test ports, lifting levers, and inspection access points. By addressing these design considerations, relief devices can be effectively integrated into pressure systems to provide reliable overpressure protection, ensuring the safety and integrity of the equipment, personnel, and the environment. Pressure relief. Relief device sizing methods. Proper sizing of relief devices is critical to ensuring their effective operation and providing adequate overpressure protection for pressure systems. The following methods and considerations are essential for accurate relief device sizing. 1. Determine the relief load. Identify all possible overpressure scenarios, such as blocked discharge, fire exposure, equipment failure, and control valve malfunction. Calculate the maximum flow rate for each scenario, considering factors such as fluid properties, system pressure, and temperature. 2. Flow equations. Use appropriate flow equations to determine the required orifice size for the relief device based on the type of fluid, gas, vapor, or liquid. 3. Gas and vapor flow. Determine the required orifice area using standard methods that account for the specific properties of gases and vapors. 4. Liquid flow. Determine the required orifice area based on the volumetric flow rate and pressure differential for liquids. 5. Two-phase flow. Two-phase flow, mixture of liquid and vapor, requires more complex calculations. Methods such as the homogeneous equilibrium method, HEM, or the omega method may be used. The HEM assumes the liquid and vapor phases are in thermal and mechanical equilibrium. The omega method uses empirical correlations to account for phase interactions. 6. Critical versus subcritical flow. Determine whether the flow is critical, choked, or subcritical. Critical flow occurs when the flow velocity reaches the speed of sound in the fluid, making the mass flow rate independent of downstream pressure. For subcritical flow, the mass flow rate depends on both upstream and downstream pressures. 7. Relief device coefficients. Use appropriate discharge coefficients for the selected relief device, which account for the efficiency and flow characteristics of the device. Standard discharge coefficients are available for different types of relief valves and rupture discs. 8. Superimposed and built-up back pressure. Consider the effects of superimposed and built-up back pressure on the relief device performance, as back pressure can reduce the effective capacity of the relief device. Adjust the sizing calculations to account for back pressure, using correction factors or back pressure coefficients. 9. Temperature and compressibility effects. For gas and vapor relief, account for temperature effects using the appropriate gas constant and temperature correction factors. For compressible fluids, use the compressibility factor to adjust the flow calculations. 10. Fire case sizing. For fire exposure scenarios, calculate the relief load based on the heat absorption rate of the equipment's wetted surface area. Use empirical formulas or guidelines from API RP 521 to determine the required relief rate for fire cases. Relief device capacity verification. Once the required orifice size is determined, verify that the selected relief device has the necessary capacity to handle the calculated relief load. Check the manufacturer's data for the relief device to ensure it meets the required specifications. By addressing these sizing methods, relief devices can be effectively integrated into pressure systems to provide reliable overpressure protection, ensuring the safety and integrity of the equipment, personnel, and the environment. Pressure relief. Relief valve location and arrangement. The proper location and arrangement of relief valves are crucial to ensure their effective operation and accessibility. The following considerations should be taken into account when determining the location and arrangement of relief valves. 1. Proximity to protected equipment. Relief valves should be located as close as possible to the equipment they are designed to protect. This minimizes the volume of fluid between the equipment and the relief valve, ensuring a quicker response time during an overpressure event. 2. Minimizing pressure losses. The inlet piping to the relief valve should be as short and straight as possible to minimize pressure losses. Excessive pressure losses can cause the relief valve to operate improperly or delay its opening. 3. Inlet piping size. The diameter of the inlet piping should be at least equal to the nominal size of the relief valve inlet. This helps to reduce friction losses and ensures adequate flow to the relief valve. 4. Avoiding piping stress. The arrangement should prevent undue stress on the relief valve and its connections. Piping should be adequately supported and anchored to avoid vibrations and movements that could affect the valve's performance. 5. Discharge piping. The discharge piping should be designed to handle the maximum expected relief flow without causing excessive back pressure. The diameter of the discharge piping should be at least equal to the nominal size of the relief valve outlet. 6. Safe discharge location. Relief valves should discharge to a safe location where the released fluid will not pose a hazard to personnel, equipment, or the environment. Discharges can be directed to flare systems, vent stacks, or containment areas. For toxic or hazardous fluids, additional safety measures such as scrubbers or neutralizers may be required to handle the discharge safely. 7. Protection from weather and environment. Relief valves should be protected from adverse weather conditions and environmental factors that could affect their operation. This includes protection from rain, snow, ice, and debris. Enclosures or weather shields can be used to protect relief valves while ensuring they remain accessible for inspection and maintenance. 8. Accessibility for inspection and maintenance. Relief valves should be located in accessible areas to facilitate regular inspection, testing, and maintenance. Adequate space should be provided around the valve for personnel and equipment access. 9. Avoiding blockage and contamination. The inlet and discharge piping should be arranged to avoid the accumulation of debris, sediment, or other contaminants that could block the valve or impair its operation. Strainers or filters can be installed upstream of the relief valve to prevent foreign material from entering the valve. 10. Orientation and mounting. Relief valves should be mounted in a vertical position whenever possible to ensure proper operation and drainage of any accumulated fluids. For valves that cannot be mounted vertically, consult the manufacturer's guidelines for proper orientation and installation. 11. Thermal expansion and contraction. Consider the effects of thermal expansion and contraction on the piping system. Expansion joints or flexible connections can be used to accommodate thermal movements without imposing stress on the relief valve. 12. Noise and vibration control. Discharge piping should be designed to minimize noise and vibration during relief events. This may include the use of silencers, diffusers, or vibration dampers. Ensure that the relief valve and associated piping are securely anchored to prevent excessive movement and noise. Fire protection. Relief valves and associated piping in fire-prone areas should be protected against fire exposure. Fireproofing materials or insulation can be used to provide protection. Ensure that firewater systems or other firefighting measures do not obstruct access to the relief valves. By considering these factors, the location and arrangement of relief valves can be optimized to ensure their reliable and effective operation, enhancing the safety and integrity of the pressure system. Emergency depressurizing systems. General emergency depressurizing systems are essential for reducing the pressure in process equipment to a safe level during an emergency situation, such as a fire or a major process upset. Proper design and implementation of these systems are critical to ensuring the safety of personnel, equipment, and the environment. Determination of depressurizing requirements. The determination of depressurizing requirements involves identifying the scenarios under which depressurizing may be necessary and calculating the required depressurizing rates. Key considerations include 1. Identification of scenarios. Identify potential emergency scenarios that may require depressurizing, such as fire, equipment failure, or loss of containment. Evaluate the impact of each scenario on the process and determine the need for depressurizing based on the risk assessment. 2. Depressurizing rate. Calculate the rate at which the pressure needs to be reduced to achieve a safe condition within a specified time frame. The depressurizing rate should be sufficient to prevent catastrophic failure of the equipment while considering the thermal and mechanical limits of the materials. 3. Thermal stress considerations. Evaluate the thermal stresses imposed on the equipment during depressurizing, especially if the process involves high temperatures or cryogenic conditions. Ensure that the rate of depressurizing does not cause thermal shock or exceed the material's temperature limits. 4. Minimum allowable temperature. Determine the minimum allowable temperature for the equipment and process fluids during depressurizing. Ensure that the depressurizing process does not cause temperatures to drop below this minimum, which could lead to brittle fracture or other material failures. Sectioning of process systems. Proper sectioning of process systems is crucial to ensure that emergency depressurizing can be effectively carried out. This involves dividing the process system into manageable sections that can be independently depressurized. Key considerations include 1. Identification of sections. Identify the sections of the process system that need to be depressurized during an emergency. Sections should be defined based on the process flow, equipment layout, and potential hazards. 2. Isolation valves. Install isolation valves to allow independent depressurizing of each section. Ensure that these valves are accessible and can be operated quickly and reliably during an emergency. 3. Depressurizing valves. Install depressurizing valves in each section to control the rate of pressure reduction. These valves should be sized and selected based on the calculated depressurizing rates and the specific requirements of each section. 4. Valve location. Locate isolation and depressurizing valves in accessible areas to facilitate operation during an emergency. Consider the use of remotely operated valves for sections that are difficult to access or have high-risk exposure. 5. Piping design. Design the piping system to ensure that each section can be effectively depressurized. Consider the use of pressure relief devices, vent lines, and discharge points to manage the flow of depressurizing gases or liquids. 6. Redundancy and reliability. Ensure that the depressurizing system has redundancy and is reliable under all potential emergency conditions. Regularly test and maintain the isolation and depressurizing valves to ensure they function correctly when needed. By considering these factors, the process system can be effectively sectioned and prepared for emergency depressurizing, ensuring the safety and integrity of the entire system. Emergency depressurizing systems. Depressurizing design considerations. The design of emergency depressurizing systems involves several key considerations to ensure that it functions effectively and safely during an emergency. The following factors should be taken into account. 1. Depressurizing valve selection. Select valves that are capable of handling the required depressurizing flow rates and pressures. Valves should be robust, reliable, and able to operate under emergency conditions, including high temperatures and pressures. 2. Valve sizing. Size the depressurizing valves to ensure they can achieve the necessary depressurizing rates without causing excessive pressure drop or flow restrictions. Use appropriate sizing methods and consider the specific properties of the process fluids. 3. Piping layout. Design the piping layout to minimize pressure losses and ensure efficient flow from the depressurizing valves to the discharge points. Avoid sharp bends, restrictions, and long pipe runs that can impede flow. 4. Discharge locations. Ensure that the discharge locations for depressurizing gases or liquids are safe and comply with environmental regulations. Discharges should be directed to flare systems, vent stacks, or other suitable containment systems. 5. Thermal effects. Consider the thermal effects of rapid depressurizing on the equipment and piping materials. Rapid depressurizing can cause temperature drops that may lead to brittle fracture or other material failures. Use materials that can withstand the thermal stresses imposed during depressurizing. 6. Control and instrumentation. Implement control systems and instrumentation to monitor and regulate the depressurizing process. Use pressure and temperature sensors, flow meters, and control valves to ensure accurate and reliable operation. 7. Safety and redundancy. Incorporate safety features and redundancy into the depressurizing system to ensure it functions correctly even if some components fail. Regularly test and maintain the system to ensure its reliability. 8. Operator training and procedures. Provide comprehensive training for operators on the operation and maintenance of the depressurizing system. Develop and implement standard operating procedures for emergency depressurizing. Evaluation of depressurizing rate. Evaluating the depressurizing rate is a critical step in designing an effective emergency depressurizing system. The following steps outline the process for evaluating the depressurizing rate. 1. Identify emergency scenarios. Identify and analyze all potential emergency scenarios that may require depressurizing, such as fire exposure, equipment failure, or process upset. Determine the worst-case scenarios that will drive the design of the depressurizing system. 2. Determine target pressure. Establish the target pressure to which the system must be depressurized to achieve a safe condition. This target pressure should be low enough to prevent catastrophic failure of the equipment. 3. Calculate required depressurizing rate. Calculate the rate at which pressure must be reduced to reach the target pressure within the allowable time frame. Consider the volume of the system, initial pressure, and target pressure. Use appropriate formulas and methods to determine the depressurizing rate, considering factors such as fluid properties, system pressure, and temperature. 4. Thermal and mechanical limits. Evaluate the thermal and mechanical limits of the equipment and materials involved in the depressurizing process. Ensure that the depressurizing rate does not cause temperatures to drop below the minimum allowable temperature or impose excessive thermal stresses. Consider the potential for brittle fracture, material embrittlement, and other temperature-related issues. 5. Validate with simulation and testing. Use simulation tools and models to validate the calculated depressurizing rates and ensure they are achievable under the specified conditions. Conduct testing, if possible, to verify the performance of the depressurizing system and adjust the design as necessary. 6. Account for back pressure. Consider the effects of back pressure on the depressurizing rate, especially if the discharge is routed to a flare or vent system. Back pressure can reduce the effective capacity of the depressurizing valves. Use correction factors or coefficients to adjust the depressurizing rate calculations for back pressure. 7. Review regulatory and safety standards. Ensure that the depressurizing rate and system design comply with applicable regulatory and safety standards, such as API, ASME, and local regulations. Document the design and calculations for review and approval by relevant authorities. By carefully evaluating the depressurizing rate and considering these design considerations, an effective and reliable emergency depressurizing system can be designed to ensure the safety of personnel, equipment, and the environment. Emergency depressurizing systems. Low temperature evaluation. When designing emergency depressurizing systems, it is crucial to evaluate the potential low temperature effects that can occur during depressurizing. The following considerations and steps are essential for ensuring that the system can handle the low temperatures without compromising safety or equipment integrity. 1. Identify low temperature scenarios. Determine the scenarios under which low temperatures may occur during depressurizing, such as rapid pressure reduction or the release of cryogenic fluids. Consider the properties of the process fluids and the potential for Joule-Thomson cooling or adiabatic expansion. 2. Determine minimum allowable temperature. Establish the minimum allowable temperature for each component in the system, including piping, valves, and equipment. Consult material specifications and standards to identify the temperature limits for different materials. 3. Evaluate thermal stresses. Assess the thermal stresses imposed on the equipment and piping materials due to rapid temperature changes. Ensure that the materials can withstand these stresses without failing. This may involve conducting thermal stress analysis or using simulation tools. 4. Select appropriate materials. Choose materials that can maintain their mechanical properties and integrity at low temperatures. Common materials for low-temperature applications include stainless steel, certain carbon steels, and nickel-based alloys. Avoid materials that become brittle or lose strength at low temperatures. 5. Insulation and heat tracing. Consider the use of insulation to minimize heat loss and prevent excessive cooling of the system components. Implement heat tracing where necessary to maintain the temperature of critical components above the minimum allowable temperature. 6. Flow and pressure control. Use control systems to regulate the depressurizing rate and prevent rapid temperature drops that could lead to low temperature issues. Implement flow and pressure control devices that can modulate the depressurizing process and maintain safe operating conditions. 7. Monitor temperature and pressure. Install temperature and pressure sensors at strategic locations to monitor the conditions during depressurizing. Use these sensors to provide real-time data to the control system, enabling adjustments to be made as needed to avoid low-temperature problems. 8. Testing and validation. Conduct testing to validate the system's ability to handle low temperatures. This may include cold weather trials or controlled depressurizing tests. Verify that the system components perform as expected under the simulated low-temperature conditions. 9. Safety margins and redundancy. Incorporate safety margins in the design to account for uncertainties and variations in temperature and pressure conditions. Ensure that the system has redundancy in critical components, such as multiple temperature sensors and backup heat tracing, to enhance reliability. 10. Review standards and regulations. Ensure compliance with relevant standards and regulations for low-temperature applications, such as those provided by API, ASME, and local authorities. Document the evaluation and design process, and seek approval from regulatory bodies if required. By thoroughly evaluating and addressing the potential low-temperature effects during depressurizing, the system can be designed to operate safely and effectively, protecting both personnel and equipment from the risks associated with low temperatures.